Welcome to part 2 of our Kubernetes concepts discussion. If you haven't watched part 1, there should be a link in the description. Please use that and go over that part because in this part, obviously, we are building on what we learned in that video. So in part 1, we did touch on the worker nodes, and we're just going to drill further into what a worker node is composed of. So one thing which the worker node has is something that's called Kubelet. This is the main Kubernetes agent, which handles all the communication with the cluster. Then there's another component called runtime. This is the component which is responsible for executing the task, as well as the very important task of running the containers. A runtime could be based on container D or Docker, or there are also other runtimes available for Kubernetes that we can configure. Then there's another component called kube-proxy. This implements the cluster networking, and it also handles the load balancing of traffic to the pods that are running on the node. We're gonna cover pods in detail as part of this discussion. Pod is a very important concept of Kubernetes. It is the building block. It is the atomic unit of scheduling in Kubernetes. You can run containers, virtual machines, WebAssembly apps in Kubernetes, but they all need to be packaged in pods. Quick note on the association of pod and containers. A simple configuration and common one is to have a single container per pod, but you also have the ability to run multiple containers in a single pod. We will go into this in the upcoming slides. Now, how do we define a pod? A pod is an abstraction. It is a shared execution environment for the containers, which could be one or more, that are being run as part of that pod. So they share that execution environment. What does that execution environment contain? It contains the network stack, volumes, and shared memory. So here you can see that we have a pod that is running two containers. This is the main container. This is the sidecar container. You're going to see in the upcoming slides what a sidecar container is. And here, what's important to note is both the containers have the same IP, and also they are sharing the same volume. So we will go into what a PVC is, but at this point, just think that this is a volume which is being shared by both the containers running within the same pod. Few more very important characteristics about pods to know are that pods are, as mentioned before, are the atomic unit of scaling in Kubernetes. So when we say we are scaling up, and here I have mentioned horizontally scaling up because you can also vertically scale up. So when we say we are scaling up, what we mean by that is we are just adding more pods. When we say we are scaling down, what that entails is just removing pods. So that's why they are called the atomic unit of scheduling. Very important characteristic is that we need to understand that pods are mortal. And the reason why it's so important for us to know is, like if you're an application developer, what this means is that, first let me define what we mean by mortal here. By mortal, we mean that they could be deleted or spun up during the anytime by the runtime as part of the scaling or self-healing activities. What that means for application developers is that we need to implement and design our applications with this characteristic in mind, that our application running within a pod could be deleted anytime, or it could be spun up anytime. Another very important principle of pods is that they are immutable. That is, they are never updated. And when we modify a pod, what that means is actually we are deleting the existing pods and spinning up new ones. We will rarely deal with pods directly. For the most part, we would be interacting with them using some high-level controller that would be managing the pods for us. For example, the deployments, stateful sets, daemon sets. Obviously, we're going to go into all of these in the upcoming videos. But for now, just keep in mind that we don't usually directly interact with pods in practice. Here is an example of how applications or pods are packaged in Kubernetes. What you are seeing here is the high-level container, which is high-level controller, which is the deployment in this case, which we were just talking about. So just skipping through these details, I'm just gonna cover the pod part. So this is the part where we define the pod, and this is within the pod definition section. This is the part where we specify the containers. So here we are saying that this pod only has one container, which is the Nginx container based on this image. Now that we have seen the YAML, let's further look into the pod lifecycle. So first, pods are created using a manifest file, which is the YAML, which you just saw. And then we publish that YAML to the API server where they get scheduled for execution. So from there, they are picked up by the scheduler and they are assigned to a node where they start running. And then from there on, whatever their life cycle is, when the application either stops successfully, or if there is a failure, or if there are any auto-scaling or self-healing activities, the pod would be deleted. So this is the entire life cycle of a pod. All pods are connected to each other using what is called pod network. So all pods get assigned IP addresses, host names, and then they can communicate with each other because they are connected using the pod network, which is an overlay. The pod network, like a lot of other things in Kubernetes, is implemented using a third-party plugin, which interfaces. So in Kubernetes, there is the concept of interfaces. And similarly, for the pod network, we use a CNI to implement networking through a third-party plugin. So in this illustration, what you can see is you have these nodes, and these nodes might have their own network with how they are connected with each other. But then there is an overlay, the pod network overlay, through which all the pods are connected. Let's talk a little bit more about multi-container pods now, because now we have enough knowledge, and this is a very important concept. So as I discussed earlier, that a pod could have multiple containers. Now, what those containers could be, there are two kinds. So a pod is always going to have its main container, and then with that, you could have one or more init containers, which are special kind of containers that are guaranteed to run and complete before the main container. And then you have sidecars. These are another kind of containers that run alongside the main container. They are guaranteed to run before the main container and then terminate after the main container. Use cases for sidecars are that, let's suppose you want to publish the logs to some external destination and you don't want to build that logic in your main application, which is a very common use case and like a decoupled architecture. So you could have a sidecar container that would be running alongside the main container, and it would be tailing the log files of the application and publishing the logs to the external destination. For init containers, the use cases include if you want to do any initializations before your main application comes up, that's where you can use your init containers. So here is a sample definition for a multi-container pod. So here we have the main container, and then here we are seeing two init containers that are running these commands. So these commands, these containers will run, and these commands would be executed before the main application container comes up. So if you look into these commands, here it's just demonstrating that maybe your application relies on some service to come up. So it's going to wait for the service to come up here, and then only stop once that service is up. Similarly, maybe your application requires a database to be up before you want to run your application. So here it's waiting for somewhere here. It's waiting for, it doesn't have that command. No, it has that command. So it's waiting for the database service to come up before stopping, so that application container only comes up once the database service is up. This is a good example of how init containers can be used in actual production scenarios. Declarative model is a core philosophy of Kubernetes, as well as the states, which is the desired state, and there are two other states which I'm going to mention. The declarative model, an example of that was the YAMLs that you saw. The philosophy behind this is we just tell the Kubernetes cluster the state we want the cluster to be in. We don't tell the how, we just tell the what. So that's what the declarative model represents. We are just telling the what state we want, not telling the cluster how. The cluster is going to figure out the how itself. And then we need to understand the relationship between the declarative model and the desired state. So declarative model is telling what we want, and this is what the desired state is. So when we define what we want in a manifest file, we publish it to Kubernetes, and that gets saved in the cluster store as the desired state. What's going to happen after that is Kubernetes is going to also be checking the observed state. And if there is a difference between the observed state and the desired state, a reconciliation process is going to happen, which is the process of making the observed state equal to the desired state. Hope this makes sense. And this is a very simple but very powerful concept of Kubernetes. The way the process works is that we are going to implement a YAML file and define what the desired state should look like. The YAML is then posted to the API server. From there, as I mentioned earlier, the desired state is recorded in the cluster store. It's persisted there. From there, a relevant controller is going to get notified about the change in desired state. And what it's going to detect is that the observed state doesn't match the desired state. And that would trigger the reconciliation process, which is the process of bringing the observed state in sync with the desired state. And this is how all containers are implemented. And they keep doing this in a loop. Not containers, how all controllers are implemented. And here is some visual representation of what I just explained. I'll just quickly go over the process again. So user wrote the desired state in the YAML manifest, published the YAML manifest to the API server. The API server records the desired state in the cluster store. From there, a controller picks up, detects the difference between the observed and desired states, and then starts the reconciliation process, which brings the observed state equal to the desired state.